All right, let me do my introduction. Welcome everyone to the Critical Infrastructure Resilience webinar series. I'm Randy Sandone. I'm the Executive Director of CIRI, the Critical Infrastructure Resilience Institute, and I want to welcome you to the presentation today, which is titled "The Implicit Interactions Analysis of a Wastewater Treatment System Case Study," and our speaker will be Dr. Jason Jaskolka of Carleton University. And let me provide a little bit of intro. And as our name implies, our mission is to improve the security and resilience of our nation's critical infrastructure. And obviously, one important aspect of doing so involves identifying and fixing vulnerabilities and potential vulnerabilities in systems. Understand that involves understanding what systems or components are vulnerable and what an attacker might be able to do in terms of reaching from one component or program or system to another. In fact, there's an entire industry that's built up around doing vulnerability scanning and assessment of these identifying vulnerabilities and seeing where they might go in a system. But heretofore, all of these approaches relied on known communications paths between components, programs, and systems. What you're about to hear is about an entirely different approach, and we think it adds significantly to the arsenal of weapons to address system vulnerabilities, and that is the notion of identifying what are called implicit interactions. Which are interactions that are not designed into the systems, were not expected, they're not foreseen, and are not known. And then categorizing the potential severity of the impact should those implicit interactions be exploited. We'll discuss and apply a formal methods-based approach for identifying and analyzing these implicit interactions in a real-world system, a wastewater dechlorination system that was provided by a municipal wastewater treatment facility up in Canada. And Jason will present and discuss his experimental analysis results summarizing the identified implicit interactions and calculation of their severity and exploitability, as I discussed earlier. All of which helps to inform mitigation efforts at very early stages of system design. Lastly, he will also discuss the validation of his model and analysis through the presentation of results of a stakeholder questionnaire, which shows that this rigorous practical approach applied in this case study has the potential to improve overall security and resilience for other critical infrastructure systems. And so let me introduce Jason and let him get on with his presentation. Dr. Jason Jaskolka is an assistant professor in the Department of Systems and Computer Engineering and the director of the Cybersecurity Evaluation and Assurance Research Lab at Carleton University in Ottawa, Ontario, Canada. Jason received his PhD in software engineering in 2015 from McMaster University, which is in Hamilton, Ontario, and he's a licensed professional engineer in Ontario. Jason's research interests include cybersecurity evaluation and assurance, threat modeling, security by design, and formal methods and algebraic approaches for software and security engineering. He's interested in applying his research to critical infrastructures, industrial control systems, cyber physical and distributed systems, and the Internet of Things. Jason, thank you very much for agreeing to give this presentation, and you can take it away. Thank you.
All right. Thank you, Randy, very much for the introduction. Hello, everyone. So as the introduction mentioned, today we're going to talk a little bit about implicit interactions analysis, and we're going to focus our discussion today on a wastewater treatment system that we recently applied these methods to and obtained results from. So just before we get started here, I'd like to make an acknowledgement that the material that I'm presenting today is supported by the US Department of Homeland Security under the CIRI banner. And the disclaimer here is that all of the views and conclusions of the presentation of the work that I'm presenting are my own and shouldn't be interpreted as official policies of the US Department of Homeland Security. So with the formalities out of the way, let's start talking a little bit about critical infrastructure. So nowadays, most of our critical infrastructures, such as those that we find in national security, in wastewater and water management, in maritime or transportation systems, in advanced manufacturing, communications, energy, the list can go on. All of these systems have grown to become very large and very complex systems. And as a result of this, it's becoming increasingly important to ensure that they operate in a safe, secure, and reliable manner. And all of this can fall under this idea of being resilient. So when we think about these large, complex critical infrastructure systems, what we find is that they consist of numerous components and ultimately even more interactions. And some of these interactions between these different components may be unfamiliar, unplanned, or unexpected, or they may not be visible or immediately comprehensible by the designers of these systems. And this is what we call an implicit interaction. These unfamiliar, unplanned, unexpected interactions that are the result of the size and complexity of these different systems. So the existence of implicit interactions in these systems indicates the fact that we have unforeseen design flaws that allow for these interactions to be present. And because the designers are generally unaware of these particular linkages, they can constitute a security vulnerability for us. And this is a problem because if these interactions exist within these complex systems, it's possible that they can be exploited at a later time in order to mount a cyber attack. And what we're really worried about because of this is the potential for unexpected system behaviors as a result. So many of these critical infrastructure systems and many of the control systems that operate within them are designed in such a way that they provide a very particular service. And if all of a sudden we can have these unexpected system behaviors, we can have disruptions of those services, or we could have the potential for unsafe or unreliable behaviors as well. So that's really what we're trying to address with this work. So we focused in on a case study system from a wastewater treatment facility. And ultimately, just about every wastewater treatment facility looks a little something like this. So the one that we have in town in Ottawa here, not quite exactly like this, but close enough for giving you an idea of what it looks like for these systems. So we have all these different tanks, they have different chemicals, different stages of wastewater treatment as well. And there are complex industrial control systems that you can't actually see in the picture here that are making this entire facility operate. So when we reached out to some stakeholders, what we got was a case study system that's just one subsystem of an entire facility. And this subsystem is responsible for the dechlorination process of the wastewater. So the objective of the system is simply to reduce the total residual chlorine in the final effluent that comes out of the plant so that it's compliant with the federal government's regulated levels. And because we have this system, you can see in the image on the slide here, we have the process control that was provided by the SCADA operators of the wastewater treatment facility. And this is basically showing what the system operation looks like and what the operator's monitoring station would look like. And what I want to draw your attention to is on the right-hand side of this image, you can see that the final effluent is actually going to a river outfall sewer. So what this means is that once the wastewater treatment is completed, we're actually pumping the water back out into the river. So you can imagine that in a system like this, if there is some sort of malfunction, disruption, anything of that sort, we're now going to be in a position to cause some environmental damage, because we're going to be pumping perhaps far too much chlorinated water into the local rivers. And that obviously is something that we want to avoid. So it was important for us to look at this system to try to identify, are there ways in which, by the design of the system, an adversary could exploit an implicit interaction in order to cause perhaps that undesirable impact or that undesirable system behavior. So in order to do this analysis, we first need to start off by modeling the system's operation. So with some discussions with the stakeholder, we developed a system model that at the high level looks like this, where we have several different components, where we have a sample pump that's taking samples of the effluent and pushing them to two different analyzers. One is looking for sulfite, which will give a reading of the residual chlorine. And one is the sample flow meter, making sure that there's a continuous flow in this system operation. And the results of this are going to a programmable logic controller, or PLC, and that's going to control chemical feed pumps that are in a lead-lag configuration in order to apply the proper dosages in order to reduce the total residual chlorine so that it's safe to pump back out into the river. And of course, there is a human operator that is involved in this as well. So if there are any alarms in terms of lack of flow or something like this, an alarm goes off and the operator has to intervene and basically send a signal that says everything is fixed and we can continue operating as normal. So in this system operation model that we have, basically what we've done is taken the control flow from the process flow diagram and mapped it into an abstract form. And here we have two different kinds of communication. There's stimulus communication, which is basically like a message passing among these different components. And then there's a shared memory among some of these components as well, which is denoted by these shared variable communications. And of course, there's a system boundary because we're only interested in what's happening within this system. And there are external influences on the way this system operates. For example, the human operator making a repair in the system. So once we have this modeled system operation, the next thing to do is to develop a formal specification of this system. So in order to do this, we use an algebraic modeling framework, which is called Communicating Concurrent Kleene Algebra, or C2KA. And this is simply an algebraic formalism for system modeling and allows us to express the influence of the stimuli and shared variable communications on the different agents or components within this system. So it basically gives us a convenient way to mathematically express the behavior of the modeled system that we had on the previous slide. And with this framework, we have three levels of specification. There's a stimulus response specification that allows us to express the influence of the stimuli on the agent behaviors. There's an abstract behavior specification, which allows us to express the possible behaviors that each component within the system can have as an algebraic term. And then there's a concrete behavior specification, which allows us to specify the actual program that is executed for each abstract behavior that we have. So just to give you a little taste of what this looks like without going into all of the details of it, the stimulus response specifications for the PLC, for example, look like these two tables that are at the top of the slide here. And what we have are basically two function tables that express for all of the different stimuli that are across the column header, when those occur within the system, depending on the specific behavior of the PLC, which is represented in the row header of these tables, what is the resulting behavior and what is the resulting output or next stimulus that would cause a continuous operation of this system. So the top table talks about next behaviors, the lower one talks about next stimuli. So in addition to that, we also have the abstract behavior of these system agents. So for example, you can see in the stimulus response specification that we have two possible behaviors for our PLC. Either it's in a proportional integral derivative control mode, or a PID control, or it's in a ratio control mode. And so that is what our abstract behavior here specifies with the plus operation, which basically denotes it's in a choice between either its PID or ratio control modes. And we can do the same sort of thing for all of the other components within our system as well. In this case, we just simply represent the choices of the different behaviors or different states, if you will, of each of these components. And then to give you a taste of the concrete behavior specification, what we have here is a description of the behavior of the PID control mode for the PLC. So basically, we have a few set points that are checking for a continuous flow rate within the system. And if it falls below that set point, we're going to send an alarm. And otherwise, we have some control logic that describes how we control the chemical feed pumps within the system in order to provide the proper dosages for the target flow that we need for our residual of chlorine. Okay. So ultimately, we specify the entire system in this way. This is simply an example of one of the components, but we do this for all of them. And then the next thing that we need to do is, in order to characterize the implicit interactions, that is, those that are unexpected within the system, we need to be able to discriminate of what we actually expect from this system. So we call this the intended system interactions. And the image that you see on the slide here is basically a representation of these intended system interactions. And what this is representing is the control flow among the different components in order to provide the system operation. So we can see here that SAP, which is the sample pump, passes control to the SO3 analyzer, the sulfide analyzer, as well as the sample flow meter. And those then contribute to controlling the PLC, which controls the chemical feed pumps, etc. So what we have here is the dashed lines represent the shared variable communication, and the solid lines represent the stimulus communication that we have in this system. So ultimately, how we derive this is we unroll that system operation model that we had by looking at the sequence of operations that needs to occur within the system in order to have the system operate as expected. So with this, every single possible path that we can generate out of this graph then becomes an expected interaction or an intended interaction within our system. So once we have that set of intended interactions, well, then the next step is to identify those that would be implicit. So this happens within two steps. So the first is that we need to determine all of the potential communication paths that exist from our system specification. So because we have the system specification, we can actually generate all possible paths that exist based on that specification, whether they're intended or not. And we have a software prototype tool that helps us to compute this, because I tried to sketch it as best as I could here on the right-hand side of the slide. This is what the communication graph looks like for the system that we have. And this is a relatively small system. And you can see just by looking at this, you can't really tell what all of the interactions are. It's a big spaghetti dish. But what the blue dashed lines are actually representing here are implicit interactions that exist in this system, that there are means for these different components to influence each other's behavior, despite the fact that we didn't actually design that into the system. So how do we actually identify those implicit interactions? Well, what we're doing is we're simply determining if a path is implicit by looking at, for any potential communication path that can exist within the system, we check whether or not it's a subpath of the intended system interactions that we have. So for example, the green interaction that we have here, which says that the SO3 analyzer by shared environment communication communicates with the PLC, which then by by stimulus communication, communicates with the operator. Well, we can find that exact path in our intended system interactions. So therefore, this doesn't represent an implicit interaction. This is something we expect to see in the normal behavior of the system. However, when we see the red one, of course, when we try to find that subpath within our intended system interactions, we find that we have this disjointed path. We can't actually form that path in what we intend to have. So this flags to us that we now have an implicit interaction in our system. So it's one thing to note that an implicit interaction exists within the system. It's another thing to know, well, how bad is it going to be for me? So we've also developed some analysis tools that are really two metrics that help us to characterize these implicit interactions that exist within the system. So the first is a measure of the severity. And what the measure of severity actually is looking at is how much of an implicit interaction overlaps with what we expect to see in our intended system interactions. So it's looking for a longest common substring that identifies how much overlap there actually is. And what this actually means and why it's important to us is that if we have less overlap, this will indicate that our severity measure will be higher. And what that indicates to us is that this interaction is actually somehow more unexpected within the system. It's something that isn't one interaction between two components that deviates from what we expect, but perhaps is much more hidden within that system. And this gives rise to this notion of severity because we can then look at the interactions that are least likely to be the ones that we would find just by examining or inspecting the system. And that can help us with prioritization efforts when we have these different interactions. The other analysis tool we have here, and again, the math is a little bit much for what I want to talk about today. I'm putting it here just to give you a sense of what the machinery here looks like. But what the exploitability measure looks at is, given an implicit interaction, what can a possible attacker do if they can exploit that interaction? What are the ways in which an adversary that can exploit or compromise the source of that interaction, what can they do in order to ultimately influence the sink of that interaction, the last component of the interaction? And why this is important is that our higher exploitability measure means that we have more ways to influence the behaviors within the system. So just to give you a simple example of this is, if I have a severity measure of 1, which is going to be the max here because this will be a measure between 0 and 1, what that indicates is that if I can compromise the source of that interaction, I can send any stimulus or modify any variable, and I will have an impact or an influence on the behavior of the sink agent of that particular interaction. So that means that those are particularly bad interactions because the adversary has a lot of power and a lot of flexibility to basically do whatever they want to have an influence in the system. The lower the severity, what we really find is that this means that all of the intermediate agents that are a part of that interaction somehow need to cooperate in order to ultimately influence the behavior of the sink. So a way you can think about this is that do we require all of the stars to align in order to send a very specific message so that it propagates through that interaction to have that intended effect from the adversarial perspective? And again, this exploitability analysis really helps us to identify those interactions that have the potential for the highest level of impact within the system. And what I want to clarify at this point is that we're not actually characterizing what the influence is at the sink behavior, what that behavior actually translates into, but rather the fact that it can influence it and it can change the behavior. So we're not characterizing how bad that can be, but rather how many possible ways are there to do that, okay? So as I mentioned, in order to automate all of this analysis, we developed a simple software prototype that performs all of these different calculations. So right now it just runs as a simple command line tool. And what we can get is a sample output that looks a little something like this. So the tool will output you the identification of the implicit interactions within the system, given the specification, as well as a measure of all of the severities of those interactions. It will also give you a measure of the exploitability, and in conjunction with that, the set of possible attack scenarios in order to exploit that particular implicit interaction. So for example, you can see the very first one here where we have an attack scenario that says alarm and repair. What this means is that if I am able to modify the PLC to respond to alarms and repairs, I can falsely send an alarm or a repair signal within the system, and I will be guaranteed to influence the behavior of the sample pump, which is a very odd thing to think about, is that I can all of a sudden change the behavior of the sample pump, which is technically upstream from the control flow with the PLC. And that's quite odd. And that's what really is helpful when we look at these different attack scenarios and exploitability analysis. So applying this to our wastewater dechlorination system, in order to identify the implicit interactions, we look pairwise at each pair of agents or components that we have in the system. So on the slide here, the red parts of the bars show the interactions that are implicit, and the blue parts show those that are intended. So I'm going to draw your attention towards the right-hand side. And you'll see a few, there's 4 short bars that all have a 1 in them. They're all blue. What this is showing is that, for example, between the sample flow meter and the chemical feed pump number 1, which is the lead pump, there is precisely 1 interaction, and that is an interaction that must exist in order for the system to operate as expected. So this is that 1 interaction that we designed in the system, and that's great. That's what we want to see. But let me draw your attention now all the way to the far right, where we have 2 red bars that have number 5 in them. So here now what we have, and I'm going to focus on the one farthest to the right, is we have the sulfide analyzer, SO3, having 5 potential communication paths with the sample flow meter. These are 2 components that really are independent of one another. They get a feed of the final of the effluent from the sample pump, and they really have no business communicating with one another. But what we find is that there are actually 5 paths in this system that will enable the sulfide analyzer to influence the behavior of the sample flow meter, which again is a very strange behavior that could occur within this system. So there's just an example of identifying these implicit interactions and noticing these really odd patterns from the system specification that we extract. Carrying this forward, if we look at the exploitability analysis, what we find is that there are actually 74 of 141 total interactions. So that's about 52%, which are identified as implicit interactions within the system. But what we find with our exploitability analysis is that 43 of those 74 are actually considered benign. So what this means is that they have an exploitability of 0. So what 0 means is that these interactions can only be exploited in a very trivial manner. So because of the mathematical specification that we have, there exists a kill signal, if you will, that can be sent by any component within the system. And that's the only way that these these 43 interactions can be exploited. And that, we argue, is a very simple thing to check for, which means that these are relatively benign interactions. Alternatively, we have 21 interactions that have maximum exploitability, which is an exploitability of 1. And as I mentioned earlier, what that means is that these interactions are those that allow for the adversary to exploit them in any way in which they want, and they're going to be successful. So those 21 are really the ones that we need to focus our attention on. And this is where the exploitability analysis really helps, because it allows us to better understand which implicit interactions we should devote our time and attention to. And ultimately, when we look at all of the different implicit interactions that exist within this system, they're the result of the potential for out-of-sequence messages or reads and writes from these different system agents. And this could all be the result of either a cyber attack or a failure of one of these components. And what this analysis shows us is that there is a lot of hidden complexity and coupling among these different system agents. And again, that gives that potential for the unexpected system behaviors within these systems. So once we've done all of this analysis, what we wanted to do was make sure that, well, does any of this actually make sense to the folks that are on the ground that are working with this system? So we did some model validation by providing detailed reports of the specifications and the analysis results to the SCADA operators that provided us with the wastewater dechlorination system. So we provided them the informal system description, the formal system model specification using the Algebraic framework, as well as all of the results that were generated by our software prototype. And each of these documents was reviewed and validated by a domain expert inspection and ultimately approved by the SCADA operators and the senior control systems engineer that operated in that wastewater treatment facility. And what they showed us is that it confirmed that our system model and analysis results were actually valid in the real world context and scenarios. Ultimately, what this said is that to the folks who actually use these systems, what we developed actually makes some kind of sense, which is great news. To further validate our results, and not just the results, but also the approaches that we used, we developed a stakeholder questionnaire that was distributed to a number of relevant stakeholders at the facility that provided us with the case study system. And the questionnaire consisted of 2 parts. There was the first part, which was talking very specifically about the results and the modeling and the analysis of the dechlorination process. So this is very much with respect to the case study, as well as the approach for identifying and analyzing the implicit interactions in general. So this is a more general understanding of the approaches that we developed and their usefulness in these contexts. So our questionnaire was completed by 6 respondents, each of which were involved in SCADA operations. And this is an important point that I'll highlight in a second, because they represent a very specific group of individuals that responded to our questionnaire. So just to quickly run through some of the results that we obtained from this questionnaire, is we first asked whether the results of the wastewater dechlorination system analysis actually matched their expectations. And we had a consensus answering that yes, it did in fact perspective on the analysis of their dechlorination process. So we also asked if the results were even understandable to them. And again, we had consensus with the yes in that case. And then finally, we asked whether or not the results were valuable. So if we provide these results of this implicit interactions analysis, is it actually useful to the team or to the organization? And again, we had consensus saying yes, and some comments highlighting the fact that this kind of analysis highlights some subtle weaknesses of certain interactions within their processes. So again, this was very good news to us because it showed that our results exceeded expectations, were understandable, and actually held value. So when we asked similar questions about the approaches in general, a little bit less about the specific case study system that we had, again, we got some validation that the approach does have value because it helps to identify some weaknesses in the processes. And then we started asking some questions about tool support. And this is where the questionnaire got a little bit interesting, because we asked if you had a tool that performed this analysis for identifying and analyzing implicit interactions, would it actually benefit your activities? And we were a bit surprised that the answer was consensus no. But then when we dug into it a little bit, we found that they were commenting saying that such a tool should actually be used by integrators and developers in the early stages of the system design, which indicated that this is less suitable for an operator where the system is already in place, for example. However, we also asked a question: if you had a tool that performed this analysis, would you actually use it? So it's not a question of whether it would benefit the activities now, but just would you use it if it was available to you? And here we had all of the respondents actually answer maybe. And again, some of the comments suggested that this tool could be used by the operators to actually verify the integrators or developers' designs. So this questionnaire was really pointing us to the fact that an analysis approach like this would be very useful for integrators or developers. So we asked the respondents to describe some of the strengths that they see with our approach as well. And then there were some comments that we find here that are rather general, saying that, well, any system that highlights potential problems is helpful. And I think the important thing to note about a comment like this is that these folks are looking for solutions, right? They're looking for help in these areas because these are challenging problems to deal with. So anything that can help to identify those problems will be useful to them. And what I found interesting as well from these responses about the strength of the system is that the operators found that this kind of analysis could be part of an internal continuous improvement process, especially if it has good tool support. You can continually be checking your system for these kinds of interactions and improving it over time. And that shows a particularly interesting use case for this kind of analysis. Now, of course, we also asked them to describe some of the weaknesses they see with the approach. And some of these are things that we were somewhat expecting and rather aware of. For example, it requires some end user expertise on the subject matter. So if we're expecting, for example, the end users to be doing all of the modeling and all of the specification in order to conduct this analysis, well, then it's going to be a little bit more difficult to adopt. So we're looking for ways right now in which we can simplify that for the end user, where we can hide some of that specification and do some transformations from design artifacts that the end users may already have. Again, the respondents took this as an opportunity to tell us that this would be much more useful for integrators rather than operators. But what it would be useful for is having this kind of analysis included in proposals from integrators that are contracted to do system upgrades. And again, that was a very interesting point to be made about where this kind of analysis can be useful. Another response mentioned that if we had ways of showing where we might be able to mitigate these identified interactions, that would be helpful, and likewise a summary of these problematic areas as a result of this analysis. So this is something we're now looking at and trying to improve on, is can we use the implicit interactions that we've identified as well as the analysis results to try to highlight or focus in on the specific problematic areas of the system design that are contributing to the existence of these kinds of interactions. So that's an ongoing piece of work right now. And then finally, we asked, do you have anything else you want to tell us about our approaches? And the comment that we got here is that if used in the early stages of system development, these approaches can identify hidden problems and perhaps provide cost savings and time savings as well. And we think that is also very good feedback to help us understand the value added by an approach like I've described today. So just to summarize a few of the lessons learned from this case study, what we found is that the approaches are actually useful in identifying potential issues early in the design of the system, and that there's promise for adoption and use among system integrators in support of their security assurance efforts. And this can help in terms of providing the evidence that's required to show that the systems have in fact been designed to be resilient to a certain class of cyber threats, in this case, implicit interactions. We also learned that there is room for improvement in terms of scalability and tool support. So we're looking at applying more efforts to efficiently use these approaches to conduct the analyses. And we need to consider as well the development of some user-friendly tools to reduce the end-user expertise requirements. So we're looking at ways in which we can build more friendly tools that will help facilitate the adoption of these approaches. And then finally, we learned that these approaches can be applied in other contexts as well, because the analogous communication and dependencies that we found in this wastewater dechlorination system are found in nearly all industrial control systems. So we think that there's a good chance that we'll be able to apply these approaches in many other contexts as well. So just to conclude here, implicit interactions analysis provides us a step towards uncovering some potential cybersecurity vulnerabilities. And this can help us with improvements to system stability, safety, and security. We demonstrated the real-world applicability of this kind of analysis, which helps us to understand the hidden complexity and coupling in these kinds of systems. And these different results can help to inform the mitigation efforts of these vulnerabilities at early stages of the system design. And this includes the prioritization of these different vulnerabilities. Because let's face it, at the end of the day, we don't have infinite time and infinite money to be able to deal with every single possible thing that could go wrong with our systems. So the analysis here can help to prioritize and help us to determine where best to spend our time and resources in mitigating the interactions that have the most potential to impact the behavior of our systems. And finally, through our validation efforts as part of the project, the approaches and the results were found to be valuable, understandable, and exceed expectations. And that is exactly what we're hoping for with the case study system that we worked on over the past year or so. And that really summarizes where this project is at now. So we're looking now to move this project forward by exploring transition to practice of the different approaches that we have. And again, there's a number of different efforts that are underway in order to do this. But please stay tuned. We're continuing the work on this project and hope to have it end user ready sooner rather than later. So just to wrap us up here, On the slide, there are a handful of publications associated with the work presented in today's presentation. These are all either published or going to be appearing very shortly. And with that, I'm going to wrap up. I thank you all for your attention, and I'm happy to answer any questions that you might have. And in order to do that, I'm going to actually stop sharing the screen so I can see the GoToMeeting now.
Any questions, anyone? Okay, apparently none. Well, wait, there's a comment. Let's see. I'll read one, Jason, from the comments.
Sure.
In the chat. What challenges do you see in scaling this up to include not just the dechlorination process, but all the many controls and sensors from different processes within a wastewater facility that may be linked and communicating with central control center?
Yeah, so this is a great question, and one that, trust me, we've thought about quite a lot. So this is a challenge. Scalability is, of course, a challenge with an approach like this. However, the benefit that we have is that the algebraic framework that is used in order to do the modeling and specification enables us to work at different levels of granularity in the system. So, for example, in our dechlorination process, we have, for example, these individual sensors like the SO3 analyzer and the sample flow meter as individual components within the system. But we could just as easily look at the wastewater treatment facility and identify the dechlorination process simply as one component within that system. So we can almost have this hierarchical structuring of the analysis. I will admit that we haven't actually done it at that scale, but that is possible within the framework to specify the system in that way. So while there will be some challenges with scalability, we think we can handle them through some modeling tricks, if you will. Of course, that's going to come with some limitations as well. You'll lose a little bit of the fidelity at the finer grained levels. But if you combine this basically at a fine grained level as well as a more broader scale and a more coarse grained level, you may be able to weave all of the results together to get a clearer picture.
Okay, Jason, there's a couple of others. Here's one.
Yeah.
Can you use the same analysis methodology to investigate vulnerabilities of physical security systems such as intrusion detection systems, electronic harbor security systems, and sensors?
Again, a fantastic question. And one that's a bit more difficult to answer, simply because I don't know the specifics of those kinds of systems. But basically, any system that will have a series of components that are interacting and have a deterministic behavior. So that's why control systems become very convenient for this kind of analysis, because their behavior is rather deterministic. We can model that and apply the analysis. Whether or not the analysis is going to give results that are meaningful in those systems, we would need to have a little bit more of a deeper conversation to identify whether or not we're capturing the system at the right level. So the short answer will be, I think so, but the devil's going to be in the details of some of those.
Okay, another one. As different systems have differing levels of resources available, is there a minimum level of resources or subject matter expertise required to take advantage of this approach?
So I can tell you this much is that in terms of resources, as long as you're capable of doing the modeling and the specification, that's where the subject matter expertise is required, which has a learning curve to it, of course. But resources in terms of computing or something like that, I mean, I run the tool on my laptop, and it takes a while, but it can be done. But the idea is the real challenge in terms of resources is having the models and the specification in order to conduct the analysis. And this is sometimes hard to get your hands on if systems have a number of legacy components that not many people know how they work or how they all fit into the system with the level of detail required in order for the analysis to be done. So I would again, the short answer to this question is a moderate level of resources, nothing too crazy, but some amount of effort is going to go into taking advantage of this approach, at least in its current form. So of course, we're trying right now to minimize that as much as possible.
Okay, great. Have you looked at an overflow event where incoming wastewater would need to be diverted and the system fails by a cyber intervention?
No, so that was not something that we looked at with this specific case study. Just trying to think if given the system specification as we have it, if we could capture something like that. I'm not sure that we can, given the level of detail that we have for this particular system.
Okay.
So that's, I guess, the answer there. Unfortunately, it's not a detailed one, but I don't think so off the top of my head.
We just received another. Have you considered the model-based vulnerability analysis or model-based risk analysis methods to simulate similar scenarios? Those have been used extensively at the Center of Homeland Defense and Security at the Naval Postgraduate School.
Yeah, so this is something that we're looking at right now is actually doing some simulation of the attack scenarios that are identified as part of the analysis to try to actually capture or characterize the potential impacts of exploits of the implicit interactions. And that is some ongoing research right now. I have a student that's looking at this currently. So we're basically exploring that idea as we speak.
Okay, great. Another audience member asked, can you please repeat the slide with the definition of implicit interaction? How easy is it to have an error in the models or specification to report false alarms? In other words, implicit interactions that do not actually exist in the system.
Yeah, so I'm just going to jump back. So here, for example, is the definition of an implicit interaction. You can probably see the screen again, right?
Yes.
So from what I understand, the question is how easy is it to have a garbage model that will tell you have a whole bunch of implicit interactions that may not actually be there? That is quite easy to do, and this is why we spent a lot of effort in this project having the model validation to ensure that we were actually capturing the system as it operates and having those stakeholders involved to validate. Because I mean, I'm not a domain expert when it comes to wastewater treatment, so I modeled the system given the information that I had, and I was checking with them quite regularly to make sure that we were on track and that we had captured the system as it operates in the wild, so to speak. But that is, of course, an issue that can arise with an approach like this. And then two, just I can see the comment in the chat here. The analyses as well that basically look at measuring the severity, the exploitability, and these sorts of things are also meant to help basically weed out implicit interactions that are rather false alarms, if you will.
Okay.
Yeah.
And another question, how is uncertainty handled in your framework? Are implicit interactions treated as certain or deterministic?
So they're treated as certain to the extent of, if we identify them, it means that they absolutely exist, and we can show a mathematical proof that they exist in the system specification. But the uncertainty part is whether or not it's actually a credible threat, so to speak, and that's what the exploitability analysis is helping us to determine. Is it there basically as a benign implicit interaction, one that's just exploited in a very trivial manner that's very easy to detect and eliminate? Or is it something a bit more complicated? And that's what the exploitability analysis is helping us to uncover.
Okay, well, it looks like we're reaching the end of the time frame. I do want to thank you very much again, Jason, for an excellent presentation and for fielding all the questions, and thank everyone for joining us and for your great questions. Very, very much appreciate that. I do want to say that we'd like you to join us again on November 12th at 1 p.m. Central. The presenter will be Dr. Iris Tian from Georgia Tech University, who will be talking about a probabilistic, resilient, interdependent infrastructure system modeling, or we call it for short PRISM, which is a software that takes as inputs basic system information of infrastructure components or assets, locations, and connectivity, and builds an interdependent infrastructure model whereby multiple analyses can be run to assess risk under varying scenarios. And this software evolved from research that she undertook with the city of Atlanta, looking at critical infrastructure interdependencies relating to water management in the city. So very, very interesting work and a very interesting application of her system modeling. So I hope you will join us for that. Again, that's November 12th at 1 p.m. Central. That concludes our webinar. Again, thanks everyone for joining us. Really appreciate it. And thanks again, Jason. Appreciate it.
Thank you, everybody.